Good evening, everyone. Thank you all for making the time to be here today. I'd like to start off the session by acknowledging the traditional owners of this land, the people of the Kulin Nations, whose unceded land we gathered today. I pay my respects to the elders past, present. We also acknowledge the ongoing connection to this land and the wisdom that is passed on from generations of Indigenous communities on the natural systems, the surrounding land, and the environment we live in today in the light of today's session. I'd like to also extend the welcome to any Aboriginal and Torres Strait Island members who are here with us in the audience. Good evening, everyone. Dear alumni, members of the Faculty of Science, students and guests, it gives me a great pleasure to always host and welcome you to these Ignitor events. So for those who don't know me, I'm Udeshka Wijewardena, or Udi. You would have received a number of emails from me. I'm the Alumni Engagement Manager for the Faculty of Science. So it gives me a great pleasure to be your host tonight. We'll move on to the formal part of the evening. I'd like to take the opportunity to invite the Dean of the Faculty of Science, Professor Jordan Nash. Please welcome Jordan to the stage.
Thank you, Udi, and welcome everyone. It's also a great pleasure to see so many of you here. We really love to sponsor these events, and I'll come back and say a little bit about that in a moment. Udi said, well, why don't you give an update on what's going on in the campus so people who haven't been around can hear a little bit about what's going on. So the first thing I'll say is it's noticeably busier. So as a scientist, I have a metric to work out, how crowded the campus is, and that's how long I have to wait in the morning for my coffee. And that one has significantly increased. And that's because I think students and staff have found that university is a really cool place to be at again, and that's wonderful. So that the environment that you may remember as alumni has returned, and the campus is really buzzing, which is a great thing. Now, in terms of the science faculty, we've had some really great outcomes in research over the last years, really good grants. One thing we're really excited about is a new Center of Excellence called Weather of the 21st Century, which will be starting this year. So the Centers of Excellence are very big national research initiatives that run for about 7 years and then bring between 40 and 50 million dollars of resources to look at a particular problem. And this one will be looking at issues to do with the climate and weather and understanding the climate system, and will be hosted by the School of Earth, Atmosphere and Environment. So it's a great thing. We're also looking, the university as a whole, as you will know, has a strategy of trying to show how universities can bring together people across lots of disciplines to solve some of the big challenges of the ages. And they've listed 3, which are climate change, geopolitical uncertainty, and healthy communities. And we are attacking the climate change and also the other 2 through initiatives that we're looking at in the faculty. One of them is a specific climate science center. So we, in addition to the weather of the 21st century, we have lots of issues where we study things in science that have to do with how the climate affects life, how it affects what's happening on the planet, the ecosystems, what we can do to measure, moderate, and understand, model these systems. And so these are all part of what we want to do in terms of engaging our scientists across many disciplines in looking at this challenge. The critical minerals you're going to hear about tonight, and we're also looking to put together a critical minerals center with other faculties, including engineering and the business and economics faculty, to understand what we as a university can do to bring minds together to tackle these sort of problems. So you'll hear more about critical minerals. I will but just to let you know, we are actually putting a center together specifically to look at that. And so that's one of the things we're excited about this year. Science has another really important mission, which is to really attack things where we don't even know what the questions necessarily are yet. So many things we talk about addressing challenges, we know there's a problem, we've got to address it. But other things we do in science are just really tackling things because we just don't know or we want to learn more. And excellence in that is really, really important, because if you want to think about transformational ideas that will help you do the next thing you don't even know you might be able to do, you need to be studying at that forefront of science. And so that's a big part of our mission as a faculty, is to keep that kind of excellence at the heart of what we do, as well as looking at how we can then engage others to transfer those ideas into solving problems we know about. So we've got two hats on. One is, working with others to help figure out how science can be helping them, and the other one is actually figuring out what's the next question, what's the answer to what we don't know yet, and really tackling those frontier issues. So if we come back to critical minerals, and again, I'm not the expert, you're going to have Andrew Tomkins and Andrew Frierdich and Vanessa Wong telling you about that. They're all from the School of Earth, Atmosphere, and Environment. We also have the head of the school sitting over there. He's also Andrew. It's not a requirement to be named Andrew, and I think we have the full set here tonight. But they're all in the school, which has put together three pieces: Earth, Atmosphere, and Environment. So it's studying the Earth, it's studying the atmosphere around the Earth, and the environment of that as it goes together. So it's a mix of what was geography, geology, and climate science put together maybe 15 years ago to make a school, and it's now a great place, one of the really, in Australia, one of the really top places to look at how these systems work together. When it comes to critical minerals, I am harking back to what my 9-year-old is doing these days, and so he's playing a lot of Minecraft. And in Minecraft, if you haven't done it, the name of the game is to find these rare elements, rare things, and you go digging around. First, you got to figure out where they are, because the game doesn't give you any hints. Then you got to go figure out how to get them, and then you got to clean up the mess you make. So pretty much, kids these days are being trained to do the finding, processing, and mitigation that you're going to hear about. So that's good that kids are getting this from an early age, but I think you're going to hear from the adults what the real life issues are in that. But they are essentially, it's the same fundamental problem that you're dealing with. We don't know where these things are to first order, but we really want them. Then we got to get them, and we got to get them as efficiently as possible. And there's a lot of techniques to do that. And then, sometimes when you go out and get these things, you make a mess, and that's something which we all have to live with. And I think it's important for us to understand the implications. So the last topic I'm going to cover, because you're going to hear interesting stuff after me, is just a bit about alumni engagement. So I really enjoy coming to these events. Our staff love coming to these events, and I hope you do too. Why do we do this? Well, I met the head of alumni engagement this week, who came and talked to us and said, do you know that your faculty has one of the highest rates of engagement with its alumni? I think we have something like 40,000 alumni altogether, and we don't engage all of them. But we do have a really good rate of engagement. And that tells me two things. One is that we're putting something out there that's attractive to our graduates, but also that you're interested in what we're doing, and we're doing things that give you an opportunity to come back and engage with us in an effective way. So we'd love to hear about more ways in which we can do that. We love when you come and talk to students. We love when you come and hear about what we're doing. And so these are part of the opportunities you have to engage. We also just like when you click yes and read the things we send out and get to know a little bit about what's happening. So please stay in touch. Udi is constantly trying to keep you in touch, and I hope you will pay attention when we have these events. You, as our alumni, as I always love to say, are the biggest impact we have on society, because those 40,000 science alumni are out there doing fantastic things that we don't even know all about. So one of the other things I said to the head of alumni relations is, can we please find out what everyone is doing? And that's a difficult task, so if you can figure out how to track down every single one of our alumni and tell me what they're doing, that would be cool. But I'm guessing that's probably, you need the IT people to do that maybe. Okay, so I'm going to now turn over to our, I think I'm turning over to Mary, is that right? Okay, so first thing I'm going to do is thank the speakers in advance, but also to thank Mary for moderating. It's wonderful to have you come here and be the moderator for tonight's event. And without further ado, I turn over to you.
Okay, so now we'll move on to the most anticipated part of this afternoon, the panel session. So I'd like to introduce Mary. So Mary is a Monash alumna. So thanks for making the time, Mary, to moderate this panel. Just a little bit of background on Mary. So Mary's completed her Bachelor of Science in Monash in 2008 with a double major in geoscience and an honours in structural geology and also geophysics. Mary currently works as a sustainability geoscientist at Newmont Global Gold and Copper Exploration and Mining Company. Mary was her first role was a geologist back in, I think, it was around 2008 when I met Mary in Rio Tinto back in the day. So it's great to have you back. So that was her first role as a geologist in Canada, exploring for IOCG uranium deposits in the northern Yukon. Spent about 8 years in Rio Tinto as a laboratory geoscientist, collecting and interpreting mineral chemistry data. And it was for multiple commodities, including diamonds, copper, nickel, lithium, bauxite, and also iron ore. That's where she's developed her expertise in core scanning and remote sensing hyperspectral data. So you can speak to her afterwards in the networking to ask her on those points if you're interested, and using its applications to the mineral exploration. Following that, she's worked 5 years with Newcrest Exploration, leading their technology and innovation team, trialling and embedding the emerging technologies for faster and smarter discoveries applied to gold and copper. In her current role in Newmont as a sustainability geoscientist, Mary applies her geoscience and innovation expertise to sustainability across the business and focuses on integrating sustainability values into long-term strategy and unlocking sustainability data for decision making. So please welcome Mary as the moderator for this evening. Thank you.
Thank you, Edie. Hello, everyone. Thank you for joining us this afternoon. I imagine you're all here for the same reasons that I'm here. We're passionate about science, and we're passionate about the planet that we live on. We're curious about its ecosystems, and we care about its inhabitants, great and small. And we know there's an impending crisis point coming. It's coming soon, and it's one of the biggest challenges of all of our generations. How do we provide the resources we need for our growing and developing society without destroying the very land, water, and air that we live in? It asks a hard question. How do we balance our increasing technology development and globalisation with fair social and environmental prosperity? At the heart of this question is the challenge of providing mineral resources sustainably. Everything we create is made of or uses mineral resources, from the cities we live in and the food we grow, to our healthcare and the food and the clothes we wear and everything in between. Mineral resources are the essential building blocks of our continued quality of life. And critical minerals are those that are in the highest demand. And that's driven by our urgent need to tackle climate change and to preserve the biodiversity of our planet. So what are critical minerals? Simply, critical minerals contain metals like cobalt, nickel, rare earth elements and lithium. And these minerals are critical components in the green technologies that will help us get to net zero by 2050. They are required in increasingly large amounts in technologies like solar panels and wind turbines, in battery storage, and in the expanding grid infrastructure we'll need for those, and also in our electric vehicles, in our increasing public transport network, not to mention in computing and automation that's required for those technologies. The renewable energy system requires orders of magnitude more metals than the fossil fuel energy system that we have now. And that is what makes these minerals so critical. And these metals can often be relatively rare in the Earth's crust. hosted in complex deposits that make it difficult for us to extract them using traditional mining methods. And the footprint mining leaves behind represents mining's impact on ecosystems that we have a responsibility to preserve and maintain. The way we have mined in the last 50 years is not the way we will mine in the next 50 years. And that change won't be achieved by small incremental changes, but by big, bold change that comes from current and new generations of experts who are passionate about sustainably mining mineral resources. Hopefully there are a few of you in the audience today. Our panel for this session are experts in 3 particular stages of the mining process, and I want you to keep these stages in mind as we listen to their presentations because they tell us a story. First, exploration, how we discover new critical mineral deposits. Extraction, how we liberate those critical metals from the rock. And remediation, how we maintain and rehabilitate the surrounding environment. Our panel are going to share with us how the race to net zero is catalysing change, that big bold change that I talked about. It's a paradigm shift in how we deliver critical minerals now and into the future. And we will also hear how Monash University is playing a role in this with the commencement of the Critical Minerals Initiative. So let me introduce you to our speakers a little bit more. Professor Andy Tomkins is Deputy Head of Earth and Planetary Sciences. Incidentally, he was also my lecturer when I was a geoscience student here at Monash, and one of the people who influenced my decision to become an exploration geologist. His research focuses on economic geology, which is all about understanding how, when and where mineral deposits form. His published work on ore deposit formation models is relied upon by exploration geologists like myself to find new critical mineral resources. Dr. Andrew Frierdich is a senior lecturer and geochemist. His work focuses on developing green technologies to selectively extract particular minerals from ores. He's currently working on grants for the recovery of critical minerals from mine waste and from tailings. And Dr. Vanessa Wong is Associate Professor for Soil and Land Management. Her research focuses on understanding how land management and environmental change in agriculture and mining impacts soil health. She studies the causes of degraded and contaminated soils and methods to remediate them. So together they will be telling us the story of critical mineral resources across those 3 stages and the key role that they play in delivering this increased demand for critical minerals to achieve net zero. Please join me in welcoming all of our speakers and in inviting Andy Tomkins to the stage to start us off.
All right, thanks, Mary. I'm going to walk around a little bit and use this. That's us 3 Mary was just talking about. So let's see how we go with this and walk around a little bit. So I'm a geologist. I used to work in mineral exploration with Rio Tinto. And so what I'm going to do today is talk to you about how our geologists are going to save the world and save us from a looming geopolitical crisis. So let's see how we go with achieving that rather grandiose goal. So for me, this is one of the easiest ways to think about it. Each car on the road produces enough CO2 to equal about its own weight every year. So if you're driving around this evening on the way home, think about the cars around you and them floating up into the air, and that's what's happening every year in terms of the amount of mass of CO2 added to the atmosphere. So we have to replace all the cars on the road, or the fossil fuel burning cars on the road, with electric vehicles. There's 1.5 billion of those in the world. That's a lot of metal, just thinking about it at a straight away like that. But then it's more than that. Look at this down the bottom here. A typical electric car takes 6 times as much minerals as a normal car. So that's a lot of stuff. And this is not just cars. We need to build wind turbines. We need solar power, all this sort of stuff. We need the infrastructure to make the electricity work. So we need to go from a conventional car to an electric car in terms of amount of minerals used for the various technologies, and from natural gas and coal up to offshore wind, onshore wind, solar PV, that sort of thing. So 13 times more mineral resources need to build an offshore wind farm. So what does that mean? That means we've already mined a lot. Now we need to mine a lot more, and we need to transition to a renewable energy future by 2050. This is starting to look a bit difficult, right? So this is a pretty big expansion of mining. So when you start to think about this as a ethical problem, we need to do a lot of mining. We need to do it in a socially responsible way and clean up after us. So this is getting pretty difficult, right? It's not only that. Here's oil and natural gas and oil refining. It's all done in the US. Not all done in the US, but a large part of it's done in the US. The US is feeling nice and secure in the old way of doing things. Now, if we go to critical minerals, a lot of it's controlled by China. Rare earth elements are the example I'm going to use a little bit more today. But it's things like lithium and cobalt and nickel and copper are processed in China. That means they monopolise the world market for that. That means if they decided to go and invade Taiwan, for example, that's going to create a huge problem politically. And so this is why it's a massive geopolitical issue. On top of all that, the rare earths that are basically used to build all the motors that rockets use, jet engines use, all the advanced technology that the military uses, that's all rare earths. So you can see the big problem that's coming here if we don't do something about this in terms of finding more of these resources outside China. So that's the geopolitical side of things. So I'm going to give you a brief overview about how mineral exploration works to give you a sense of what our geologists need to do to solve this problem. So there's a geology map of Australia. Your job as a geologist is to take a map like that and then go, here's the best spot that's maybe the size of this room across as a target on the surface. Some mineral deposits have a target that big. Others can be a few hundred metres across. So that's what your job is, an exploration geologist, is to narrow down like that. So you can use geology, you can use geophysics. This is a magnetic map of all the different geological features in Australia. So some of our people in our school are geophysicists, and Mary would have done this for her honours project, wouldn't you? Yeah. So what I'm going to do is zoom in on that yellow box up the top there. That's a simplified geology map of part of Mount Isa, which has a lot of mineral deposits in it. And you can see it's starting to look a bit more complex now. If I zoom in on that box there, this is a geology map that's been simplified at 100,000 scale. And so that's starting to look a lot more complex. And then, so the other boxes on that diagram are tenements that a mineral company has selected to do mineral exploration for copper, I think, in this particular example. And so the geologist's job is to focus in on those little areas and then decide within all those little boxes which are the best places to go and take some samples and drill a hole, all that sort of stuff. So to do all that, you need to use science to get there. So all of that science is basically orgenesis models. You need an understanding of how the mineral deposits form, why they form, where they do, when they formed, all that sort of thing. So here's it's actually fairly complex, an explanation of how mineral exploration for copper works. This is a cross-section of the Earth's crust through the Western South America, where the oceanic crust is being subducted under the Andes. So there's a whole bunch of geology that's gone into understanding what's going on here. Basically, water gets into the oceanic crust gets subducted, water gets liberated from there, goes into the mantle, melts the mantle, you generate magmas, that carries metals out of the mantle, carries it up into beneath a volcano and forms porphyry copper deposits. I just explained about 4 decades worth of work in 5 seconds. So that's where they form. So down where all those green dots are, those are some of the world's biggest porphyry copper deposits. And we know how to find those. We know the right sort of tectonics to choose. We know the right timing of all the magma processes that form these things. So that means now, after all this many decades of work, we know how to go and spot these things. This is about 60% of the world's copper resources come from this type of deposit. This is production for different metals. So we've got zinc, lead, copper, steel, gold, nickel, all those sorts of common things that we're used to thinking about, normal metals that we're used to thinking about. For that period there, 1980 to 2000, that's the number of scientific articles that have been published focusing on those types of metals, common metals that we're used to thinking about. So that's 20 years of publications in one journal, and there are about 3 or 4 of these journals. So then if you think about 2000 to 2020, there's another stack equally as thick as that, and then there's another 4 journals of this. That's a lot of scientific work. So that's what I do. I publish in that. I used to be an editor for that journal. We generate exploration models for new mineral deposits. What's the situation with rare earths? Rare earths is one of the most important things. When I did, about a month ago, I did a Google Scholar search where we search for which publication has been published on a particular topic. You can see the search query that at the top says clay-hosted rare earth elements in Australia. And what did I get? I got one that's been published a month or so ago. I get one from Malaysia. None of these are relevant. And I get one review paper from 2020. That's all there is compared to that massive stack of scientific publications. That's crazy. So how are they going to find this stuff? They don't know how they form. They have no idea. That 2020 paper looks like this. You can see there are some white dots representing ion absorption clay type rare earth element deposits, a particular type of deposit I'm going to talk a little bit about. They're all in South China. There's some in a few other places as well. They form by weathering of rocks. So this is how rocks weather. We know that you might start out with down here with a granite. Gradually the water gets in there, turns all the minerals in a granite into clays, and we know that rare earth elements move downwards. You can see the red arrows there move downwards in the weathering profile to become concentrated in a particular layer. So we know how that works for China. But in that time since 2020 and now, this is December 2023, there's been heaps of new prospects of rare earth elements hosted in the weathering profile found in Australia. And you know how they find them? Some of them have been found by gold explorers drilling a hole in their backyard, going and just testing it to see if it's got something else in it, going, oh, look, there's rare earths here. I've found a deposit. That's crazy. You don't do exploration that way. The way we do it these days is use science to target down on specific areas. So that's the situation we're in. So we're heading towards, we need to build exploration models to try and do this better, to try and find the biggest ones that can be extracted more easily, doing the minimum amount of environmental damage and that sort of thing. So my colleagues are going to talk next about how to get the stuff out of these sorts of deposits and then remediate them. And that's a fundamental part of what we do next. You do the exploration, and then that's all considered in the light of those two other things. A whole bunch of questions there about what we need to do. That's where we're going with the research. We need new people to learn how to do this, so that's PhDs and postdocs all need to learn how to do this stuff. Going back to this ethical dilemma, we need to do this, otherwise we're going to keep burning fossil fuels, right? So there's a lot of mining we need. One way to stop doing so much mining is to go nuclear power. That's, you can see, is a lot less intensive in terms of the minerals it needs, and it's less intensive in terms of the ongoing mining you do after you build the thing. So yeah, that's the debate that the public has to have about what we're going to do. We probably need, in my opinion, to do some nuclear. Geologically, we know how to solve the waste storage problems. So anyway, I'll leave it there and hand over to Andrew next. He's going to talk about nickel in and how you get, and how it relates. It's similar in some ways to the rare earth element thing. Actually, it forms through a weathering process. So I'll hand it over. Do you want this or do you want that?
I'll stand up here.
Okay.
Great. Thanks, Andy. All right. Good evening, everyone. Thanks for coming tonight. It's a real pleasure to be here and to have the opportunity to talk about some of the work we've been doing to make nickel processing more sustainable, but also to use nickel waste as a way, well, I guess I should get to my title slide here. Sorry about that. But also how to use nickel waste as a way to remove carbon dioxide from the atmosphere. So I want to quickly draw your attention to this image here on my title slide. So I was just playing around with AI, and I was curious what AI thought about what I do. So for the prompt, I literally typed in my title, Lowering Carbon Emissions from Nickel Mining, into an image generator. And this was the output. You can see AI made it because it has silly things like these orange icons, which have no real meaning. But it didn't do all that bad of a job, really. It has it has some windmills here, which are made of stainless steel, which contain nickel. It has a large industrial-looking facility there in the center, and it turns out that processing plants for nickel deposits are very energy-intensive and have a lot of emissions coming out. But also, nickel mining can generate a lot of waste rock and mine tailings. And it turns out we can actually utilize this waste as a way to remove carbon dioxide from the atmosphere. So I'll talk more about that in a moment. But I first want to acknowledge that this is a very large team effort. In the interest of time, I won't go through everyone's contribution here. In fact, there's another 10 postdocs or so overseas that aren't even listed. But I do want to thank the Grantham Foundation, which is a US-based philanthropy. They've been very generous in their financial gift to help drive this work forward. We're also working with a US-based startup, Travertine Technologies, and we've been able to acquire funding from the Advanced Research Projects Agency, which is administered by the US Department of Energy. And we also have some funding from the Australian government as well. Okay, so as Andy nicely pointed out, mining is essential for producing the materials that we need for renewable energy generation as well as energy storage. But mining itself emits a lot of greenhouse gas emissions as well. So the extraction and processing of metals contributes about 7 to 8% of global greenhouse gas emissions. And when it comes just to nickel mining, we'll need to double that amount of mining just to meet the future demand for things like electric vehicles and batteries. So the Australian government has legislated that we're going to go net zero by 2050. Even if we went net zero today, the IPCC estimates that we still need to remove around 100 to 1,000 gigatons of carbon dioxide from the atmosphere by the year 2100 in order to limit warming to 2 degrees Celsius. So even if we cut all emissions to zero, there's still excess carbon dioxide in the atmosphere that needs to be removed. And one way in which we can carry out that removal is to utilize mine waste, such as in the image here. So this is the Cosmos nickel mine in Western Australia, and this is just an example of the amount of material that they produced. And it turns out these rocks are actually really useful for removing CO2. But first, in addition to using mine waste to lower carbon emissions, we also need to have more sustainable, less energy-intensive ways to actually process the nickel materials that we have as well. So how are nickel deposits processed? Well, it depends a little bit on the type of deposit. Nickel ore tends to exist as nickel sulfides. So these are deposits that form underground under high temperatures and hard rocks. The other type of nickel deposits are what we call nickel laterites. Laterites are formed from the weathering of rocks over geological timescales. And as rocks weather, soluble elements tend to leach away. And the residual material that's left behind usually consists of things like iron oxides or rust. And those iron oxide minerals can scavenge trace amounts of nickel and cobalt and enrich them over time to form an economic deposit. It turns out, though, that nickel laterite deposits are very difficult to process. Okay, typically, processing plants use something known as high-pressure acid leaching. There's a lot of capital expenditure required to build these facilities. They use a lot of energy. They produce a lot of acid, which is used to actually dissolve the iron oxides to liberate the nickel metal from within, and then that has to be neutralized. This is a photo of a plant in New Caledonia processing ore from the Goro mine. And if you look at this area right here, that's actually a 100 megawatt coal-fired power plant which runs this facility. And this facility, to put it into scale, well, before I go there, I should note here that to run these nickel processing facilities, depending upon how you do it, they can generate anywhere from 10 to 100 tons of carbon dioxide per ton of nickel produced. And typically, the laterite facilities are closer to the high end. So if we look closer, we can see why the carbon emissions are so intense. So this is the same facility, just a different perspective. And the size of this is roughly 1 by 1.5 kilometers. It's about the size of the Melbourne CBD. There's a large pile of coal, which is used to power the entire facility. We have a big pile of sulfur there that's eventually converted into sulfuric acid, which is used to dissolve the laterite at temperatures exceeding 200 degrees Celsius at really high pressures. And then, once you have all that stuff dissolved in acid, it has to be neutralized so that you can separate out the iron from all the good stuff that we want, like nickel and cobalt. And so we need something to neutralize it with, which in this case is limestone, which is made of calcium carbonate. So when you combine calcium carbonate with acid, you put CO2 into the air. So this large black and large white pile is eventually just going to go back into the atmosphere. Surely there's a better way. So we are working on different approaches to try to liberate critical metals from these types of deposits. A lot of my previous work, about a decade ago, was interested in preparing these iron oxide minerals and putting metals like nickel in there and to see if we can get it out. And it turns out that whenever you expose these minerals to iron 2+, which is a soluble form of iron, that can actually catalyze the recrystallization of these minerals. And during that process, nickel can be released. This is important because this process can occur at ambient conditions like room temperature and neutral pH. So in an ideal world, instead of ripping everything up and cooking it at really high temperatures, we could just put iron 2 in and get nickel out with minimal land disturbance. That's the ideal situation. But does this actually work for real nickel laterite ores? Well, we tested that. We took some nickel laterite ore, carried out a very simple experiment, just put some in a test tube, put some water in there, neutral pH, room temperature. So in just plain water at neutral pH, very little nickel comes out. That's not surprising. It would be nice if we could just wash these materials with water to get all the good stuff out. In the presence of iron 2+, we can see that nickel solubility increases by over an order of magnitude. So we're only getting about 5% out, which the yields are lower than we would like, but still it's very promising considering that we put very little effort and energy into this process. And with a few improvements we've been working on, we can get the yields up a bit higher than that. But what's really cool is that another critical metal, cobalt, we can actually extract the majority of that from this same reaction. So it's sort of a silver lining or a cobalt lining in that regard, that we can get two metals for one. So we are working on ways to reduce the energy intensity and thus carbon intensity associated with processing. But one of the projects that we're currently working on is actually trying to use mine waste as potential to extract additional critical metals while simultaneously mineralizing carbon dioxide. And so this is a schematic of that. We're working with a startup in the US they have some IP to generate sulfuric acid using an electrolysis setup. It produces sulfuric acid as well as sodium hydroxide simultaneously. And we're using that sulfuric acid to enhance the weathering of waste rock or mine tailings from nickel sulfide mines. Okay, so if we have a big pile of waste rock, we can put the acid on there. That enhances the weathering, essentially the same process that forms natural nickel laterites, but we're making it happen on a much faster time scale. During that process, these types of rocks have a lot of magnesium. And so magnesium is leached out, and with that sodium hydroxide and carbon dioxide from the air, or if you have a concentrated CO2 stream, that would work as well, we can form a magnesium carbonate solid. And effectively what we're doing here is we're taking CO2 in the air and turning it into a solid mineral that can be permanently stored. But quite interestingly, tailings often contain quite a bit of residual nickel and cobalt that the mining companies can't always fully recover during their own processing techniques. And so during this process, we actually generate artificial nickel laterites in this process. We're actually generating these artificial nickel laterite deposits with cobalt and nickel, which we can then further process. So where to from here? So we're past the proof of concept stage. We can, in a lab at Monash, we can put this waste rock material in a column, put some acid on there, and we can get some metals out. This is a picture of that artificial laterite that we've generated. It contains ore grade quantities of nickel in there, and when we actually process it using our approach I discussed earlier, we can get about 75% of that nickel out. And so these artificial laterites are actually much more reactive than the natural ones, which is pretty exciting. But next steps, we really need to scale up this process, find applications, and we are doing that. As scientists, it's very easy sometimes to come up with ideas and to tinker around in the laboratory, but to turn the idea of taking waste rock, turning it into a pile of rust that contains nickel, and then taking that nickel out and building renewable energy infrastructure like stainless steel wind turbines is a bit more difficult. And so we're currently chatting with industry now to try to move this from the gram or kilogram scale up to the multi-ton scale on an active mine site. So be happy to chat about that more during the Q&A. But otherwise, thanks for your time, and I'd like to bring Vanessa up for the next presentation.
Thanks, Andrew and Andy. Before I begin, I'd like to also acknowledge the traditional owners of land which this knowledge was developed, because they were Australia's first land managers and soil scientists. So what you've heard already is that the processes of exploration, extraction and processing can cause quite significant environmental damage. And that's really, that's fundamental really to these processes. What we also know, particularly about some of these critical metals, is that they can also occur in environmentally significant environments or landscapes, and they're much more difficult to extract. So with all of this in mind, how do we clean up this mess? Or how do we fix the environment after we've extracted and processed our critical metals? So in terms of mine remediation, once we've extracted and processed and disrupted the land surface, we need to somehow put it back to a form in which the majority of people are comfortable with. The mining operations usually stockpile small volumes of topsoil, and topsoil is fundamentally important for plant establishment and plant growth, so that we end up with a functional ecosystem. It also generates large volumes of waste rock and tailings, which Andrew has just spoken about. So we have a lot of waste materials and not a lot of soil. Remediation activities need to convert these waste materials into a functional soil ecosystem. So soils aren't just an inert material beneath our feet. They are actually a functional soil ecosystem that can support an above-ground environment or above-ground ecosystem, which includes vegetation and interactions with fauna. What we need to do in terms of remediation is to accelerate what we call pedogenic processes, because we're effectively starting from zero, where we've scraped clean the land surface, and we need to accelerate the processes of soil formation, like the processes of mineral weathering, formation of soil aggregates, and also get that nutrient cycling going and kick-starting microbial activity for biogeochemical cycling. And importantly, the remediated area needs to be consistent with the surrounding environment, whether that's agricultural land that we can farm again, or a conservation area, a national park or a World Heritage area. It needs to be consistent with what is surrounding that current site. And something to keep in mind is that remediation doesn't just happen at the end of life. It usually takes place during mining operations, and also and continues on after mining operations have finished. So with all of this in mind, we need to take a few steps back and look at how do we build, or what do we need to make sure that we have a functional, resilient ecosystem. And if we look at some of our ecosystems, particularly in conservation areas, what we have are 4 different stages, or four different components which make up our ecosystem. The bottom part, these bottom stages are largely they form the base of our ecosystem. So the influence of climate, how we build the landforms, and the influence of the geology. They all influence what we call this functional stage. And so in terms of how ecosystems function, they need water, high water quality, they need a functional soil ecosystem, and also water needs to be able to move through the landscape. And these bottom two stages are what we call our abiotic components. And our abiotic components are really the starting stages in terms of how we remediate a mine site or a highly disturbed environment. Once we get that right, then if we look at planting of vegetation to establish important habitat, to encourage fauna to return. What usually happens is that we focus a lot on this landform and geology component in terms of building the landform, making sure it's a really, really stable landform that is stable for in the order of tens of thousands of years. And then we launch into this vegetation component. And the vegetation component is important because we start planting vegetation or start planting trees. If we don't get this functional part right, then the vegetation is probably going to fail, or you won't have successful regeneration and revegetation. And so what we need then during these different stages and during the stages of mine site remediation is to set our landform, make sure we have our functional stage operating properly before we get into the vegetation and planting of the vegetation, to build on each of these stages so that we end up with a self-sustaining and resilient ecosystem. And so what I'm going to focus on is this functional stage here, because the geotechnical stage, as I mentioned earlier, we generally tend to focus on as the first stage in terms of remediation, and then the vegetation and habitat part we monitor really, really well. But this functional stage we know a little bit less about, and we tend to skip over it. And that then takes us back to how do we make sure that function returns, and we then go back to the basics of soil formation. And soil forms as a function of climate, which is impacted by parent material, which is impacted by climate, organisms, relief, and mediated by time. And so basically, these are the fundamental processes that occur during soil formation. If we look at what we can influence during remediation, and I'll get back to this picture in a moment. When we're looking at terraforming, or when we're looking at formation of our landforms, we can influence the relief of a particular site. The parent material of a particular site is influenced by where we put that material. So the parent material is a starting material on which soils form. And at a mine site, that includes your bedrock, it includes sediment, it includes waste rock, and it includes tailings. So using this parent material, we can form our landforms. And then we start to plant. And so the organisms then start to introduce organic matter, and they also start to introduce some of the microbial processes and the microbes that are really important to kickstart nutrient cycling. But ultimately, we want to speed this up because soil formation occurs in the order of centuries to millennia, and we want this to happen in the order of years to decades to make sure these environments or these ecosystems really establish, and then they become resilient. And what this figure shows here is the processes of soil formation, starting from your parent material, and in this case, you've got your waste rock, your bedrock. It could be your tailings. The introduction of organic materials, and these organic materials start with your mosses and lichens, and they introduce organic matter, which starts your microbial cycling processes, which then forms the beginnings of a soil profile. And so the beginnings of the soil contain the nutrients for plants to establish and to grow before a full soil profile forms, but also importantly allows for vegetation to establish, it allows for vegetation to grow, and it also then starts to store carbon, both in terms of the form of organic carbon, but also can potentially store inorganic carbon, which is what Andrew alluded to earlier. And And if we take a closer look at what happens, it's not just about introducing nutrient cycling into these soils. We need to also make sure that the physical properties are formed largely to allow water to infiltrate into these profiles, to allow plants to access deeper stores of water for during drier periods. So soils are a functional ecosystem. They contain a number of different components. They contain they're made up of soil chemical properties, which is really important for plant nutrition, which most people are familiar with. But people are less familiar with these soil physical properties. And these soil physical properties, which is in the form of aggregation and forming of soil structure, is important for water availability, infiltration of water, and also water storage, which allows plants to access water during drier periods. And importantly, because it's also a functional ecosystem, soils also have measurable biological properties, and that's really what causes the nutrients to become available from decomposition of organic matter. In terms of the limitations to plant establishment and the restoration of our soil ecosystems, there's a whole range of what we call soil constraints. And at the top of the list is contamination of both, which is made up of both organic and inorganic pollutants. And as Andrew has also alluded to earlier, can some of these critical metals be recovered from waste materials such as tailings? And it's not just nickel, but we can also look at rare earth elements which are contained in some of these waste materials. But importantly, these rare earth elements and also some of these critical metals are contaminants in our soil profile. So plants don't actually like having these around. And then there's a range of other challenges which can be the result of extraction, can be the result of processing as well. So managing the acidity in the soils, alkalinity, so high pH soils, your redox conditions, which fluctuate according to water levels, but also that influences oxygen availability for microbial cycling. Sodicity, and also salinity, which is the high concentrations of soluble salts. And so once you have some of these soluble salts in the profile and they become liberated, are these potentially of value as well? And so all of these need to be kept in mind in terms of remediation and how we overcome some of these soil constraints to ensure that we remediate or convert an area that looks something like this to be consistent with that surrounding landscape. And so I'll leave that there and hand over back to Mary.
We've come to the Q&A part of the session this afternoon, so I might ask Vanessa and Andy and Andrew to come back up to the stage. We're all going to sit in our comfortable chairs, and this is the time to think of those fantastic questions that I'm sure have been percolating in your minds. Anyone is welcome to start us off. Great. Yes, please.
Thank you for that really interesting presentation. I was just wondering, once quite a lot of the minerals have been extracted, how will the graph then plateau at all? Will you be able to reuse or recycle the nickel and other minerals? What are we looking at?
Yeah, I can have a go at that one. So it turns out that our chemistry department at Monash is doing exactly that problem. So their goal is to think about how to recycle everything. So we need to do the recycling stage of things progressively as all this is extracting enough metal to achieve that target. So it needs to increase the amount of metal, plateau, just like you said, and then be recycled. So hopefully we'll stop mining at some point in the future and stop making such a mess. But yeah, exactly what chemistry is doing. So hopefully they can figure out how to do that well.
I might comment on on that as well. I agree with Andy. I can't speak for all critical metals, but for most of them, there's plenty of them out there. We know where they are. Some of the challenges, though, are getting them out efficiently as the quality of ore deposits degrade.
And I think the Monash's Critical Minerals Initiative is going to incorporate the engineering side of that, which is going, I'm sure, to incorporate materials design and product design that has that circular economy of recycling in mind, because I think that's a key part of it. Is there anything you wanted to tell us additionally about the Critical Minerals Initiative, Andy, and the sort of work that you're hoping to be tackling?
Yeah, so the Critical Minerals Initiative, we're just from one school. We're trying to get engineering together with us, and chemistry is all part of this as well, to deal exactly with what you just said. The engineers are, designing new membranes to try and process these things more efficiently, less energetically. We need to bring in social scientists to help us deal with the ethical issues, and business people to help us figure out ways to collaborate with business community and deal with some of the business problems that come up with this. There's a lot going on to try and build a community at Monash to try and deal with all these interacting problems. So your sort of question is exactly the sort of question of, like, I can't solve that by myself. I need to interact with a whole bunch of other people to start dealing with that. Yep.
So why then, thank you for your talk, it was really interesting, but the shocking sort of picture of your black lump and your white lump and all the stuff going up, should we not, before we start mining, have some solar energy or something like that so that we don't have black lumps and white lumps? Well, black lumps anyway, and
Well, absolutely. We certainly need materials like nickel to simply build renewable energy infrastructure. Nickel is important for stainless steel, which can make wind turbines. It's a critical component in batteries to store renewable energy. But I think what your question was getting at is, can't we power these facilities with carbon-free energy? Yeah, absolutely. I'm not an engineer or an expert in energy generation, but I'm not sure of whether solar panels and wind turbines could power a facility that needs to run 24 hours a day, 7 days a week, because renewables are intermittent. The sun doesn't shine at night. But certainly, as Andy mentioned, nuclear could be an option to power large industrial facilities like this.
But to get our whole system running, and from now onwards, we've got to include in getting the rare metals, not extra pollution in ways that we already know we can do, like Finland.
Yeah,
So
I agree.
So the minerals industry is starting to do this. So I think the Cadia mine in New South Wales uses quite a lot of renewable energy to run its mining. The problem is, this is one reason why we need Australia to do it, right? Because the other countries are not doing that. They don't.
We have a lot more area for solar.
Yeah, exactly. Exactly. And some of the other countries don't care about the damage they're doing so much as Australia does. So, we need to do our bit really well so we can lead the world in how to do it.
Yes, hi. Fantastic to listen to the presentations here tonight, and I know we're all alumnus of Monash. So my question actually goes back to the process of science. So, Andrew, in your first presentation, you were calling out the absolute paucity of science that's been done on clay-derived something.
Rare earths, yeah.
Rare earths.
Yep.
And my question is, how is the science being driven? I know there's a lag in terms of getting good science research, but that to me would point out some sort of failure of the science process in terms of encouraging the right research to being done. Either it was being overlooked or it was being underfunded. What's your view on the process of the science?
Yeah, and funding the science. So it's been interesting the last 5 years or so. A lot of the funding is going to Geoscientist Australia and CSIRO, which are the government departments. And the universities have almost been explicitly excluded for some of this. But now CSIRO's turning around and going, actually, we need to talk to people like me and these guys who my job is to do the mineral exploration model development, and those guys it's their job to communicate with industry about things. They don't do that much of their mineral exploration model development, so they are recognising that they need to work with the universities to try and solve some of these problems. And it will go across the board with engineering and exactly what these guys do as well. There needs to be done better in Australia. It's not done well at the moment. The government hasn't realised how important the universities are in moving this forward.
I might also just add to that. There are falling enrolments in earth sciences globally from the undergraduate level, and that's sort of something that we really need to address because we're losing expertise and capacity in this space, and it's a matter of how to attract new students into these disciplines. And then once you look at some of those areas that Andy was talking about in terms of the ion absorption deposits, we're looking at materials that are unconsolidated and people who have expertise in regolith geoscience, and that's an even smaller group in Australia, and that I don't think there's any university at the moment that's teaching regolith geoscience.
Yeah, that's
so
right.
It's a big challenge.
So in my opinion, one of the most important roles universities play in society is not me going and talking to the minerals industry about how to do something better. It's actually me teaching the next generation of scientists so that when they go and get a job, they're bringing that knowledge with them, and that knowledge is gradually transferred to the minerals industry. So that's probably the way it mostly happens in reality. It goes across the whole scientific community then. So that's why we need to make sure that training part of it's really strong as well.
Yeah.
I can throw to the person with the microphone. Oh no, we've got two.
Here too. Hi.
I'll go to yourself.
Thank you.
I do recognise the person up the back in yourself.
So thank you very much. I learned a lot. I'm a chemist and engineer, not a earth scientist, but that was really fascinating, so thank you. But a comment and a question. The comment about doing it better. WA is already installing solar, wind with large-scale batteries, so flow batteries up in the northern WA. It's already happening in Australia. We are well and truly doing that, and the government is very well and truly trying to do clean, ESG goals are very, very high for minerals. That's fantastic. I think that's important. The second question really is, I know that in the rare earth space, which is super important for the transition, every wind turbine's got kilograms of rare earths, every EV's got kilograms of rare earths, super important. We do have two companies in Australia, Lynas and Arifera, right, who shipped everything offshore to Malaysia and did everything over there. And now then Malaysia says, no, thank you, we don't want to do this anymore, it's a dirty industry. So two questions. First of all, can we do it better in Australia in terms of the refining aspect? I know you're not refining people, but the refining aspect. And secondly, what are the types of minerals that are you aware that Lynas and Arifera actually have in Australia? Are they what you've been discussing? I'm just curious.
Yeah. I was just wondering if they wanted to say something as well. But so the Australian government has invested something on the order of $2 billion in a new refinery at Eneabba in Western Australia to process heavy mineral sands that contain things like monazite, which contains rare earth elements, that sort of thing. So there's investment going into it in Australia. You're right, it's chemically challenging to process some of these things. And it's not done very well it's environmentally damaging when it's done in China and Malaysia, that sort of thing. So I think another reason to bring it to Australia, we will do it cleaner in Australia. One of the problems for Australia is our labour costs are very high compared to Asia. And so that's a challenge. I'm not sure how, that's probably quite difficult for the government to get around that one. But yeah, that's part of the reason to bring engineering into this, because they're the guys that figure out how to process it better. So if we can get those guys if they can figure out how to process it cheaper and more in a cleaner way, then that's really what we need.
Thank you. Great presentations. I don't want to give away my age, but I'm an alumnus of 68. And in 73... I was tasked, having shifted from the laboratory in the mining industry to foreign affairs in Canberra, I was tasked with looking at a report that was then called the Club of Rome report. Don't know who in the room might know about it. But in 73, that report was suggesting, international group of experts that we were going to run out of critical minerals, not my term critical minerals, but general group of minerals, within 12 to 15 years. And I was tasked with saying, well, hang on, where does Australia stand in all of this? Because we're a big mining country and, gee, we got a lot of this stuff, don't we? And what was missing from that analysis was the application of economics. Mm-hmm. That the rarity of minerals, or the scarcity, I should say, in economic terms of minerals, is an economic factor, not a geological factor. And here am I, well past the end of my career. I started out as a chemist, I'm now a generalist. So I want to congratulate you, Andy in particular, for mentioning the term geopolitics. Because if I can offer a recommendation in the teaching of the next generation of geoscientists and others who will help us through all of these challenges that you've mentioned, it is that before they leave Monash, they need an infusion of some generalisation knowledge, or generalist knowledge. Economics, politics, international law, just to understand why these issues become so complex and why, in the case of rare earths, China stole a march on the rest of the world by buying up all the minerals which are still mined in places like Australia, but they're processed in China. So talk to your engineering, by all means, and get some smart engineering processes going so that we can process them back here and supply the world, because that'll be where the next generation find their jobs and where we can generate the wealth that the country needs. Sorry, it was a long comment, but if anyone wants to add to that, I'd be pleased to hear.
I kind of like that comment because I'm a generalist myself. I kind of like doing lots of different types of science, and I think that generalisation type stuff is really important. One of the cool things about Monash is the students can do double degrees. The better students can do double degrees. So we have science eng students, we have science commerce, we have science law, all sorts of stuff like that. So some people are coming out with almost exactly what you're looking for. It's a pity you can't do science, law, commerce. Be kind of cool. Yeah, you can do it in postgrad. Yep.
I might throw in a question of my own before going to the next one. Vanessa, I wanted to ask you a bit more about that soils regeneration section of your pyramid that you talked about. Can you give us any examples in mine remediation where that's been done well? You mentioned that it's not common. What does it look like when it's done really well?
Interestingly, I'm involved with reviewing the science in the remediation of the Ranger uranium mine, and that globally is basically best, or I would consider best practice in terms of the engagement with community, the working together of multidisciplinary groups, and working out where our key knowledge gaps are, and trying to understand those key knowledge gaps, using the science to address those knowledge gaps, and then setting up a monitoring program for that. And so what we've seen is some of there was one picture there where they set up a trial of what they call a trial landform. And the trial landform was exactly, they stepped through that process in terms of building the landform, establishing what was required in terms of the plant nutrition needs, planting out the plants, and then from there monitoring the recolonisation, in particular of the microbes, and understanding the structure and the function of those microbes as the plants developed over time. And so now this is a long-term trial. So some of those plants were planted back in the mid-2000s, and now we have a longer-term data set that we can go back to in a small site. On the mine site, which can now be applied broadly across the whole area.
And that must be really important to be able to start gathering data on long-term data on what that looks like. I'm just going to stand up because I'm missing a whole quadrant of people over here. Please, hello, yes.
Thank you.
Beg your pardon.
I have one too.
Please, thank you. Yes, and you're welcome to have a microphone if you might be able to project.
I'd just like to sort of make a comment about remediation. That although it was nice to hear the theory of remediation, the reality is, the harsh reality is that in Victoria, the number of mines that have been successfully rehabilitated is either zero or horribly close to zero. And one of the problems is not only are the mining companies can get escape from having to rehabilitate through various mechanisms, but the government doesn't seem interested in enforcing rehabilitation. I mean, they have the Earth Resources Regulator, which should be doing this, but it acts more like a toothless pussycat and fails to enforce proper rehabilitation. So do you have any way of sort of overcoming this to progress rehabilitation?
So you're right, there are thousands of legacy and abandoned mine sites in Victoria. A lot of those have been mapped, and they're highly unlikely to be rehabilitated or remediated to a standard that is consistent with the surrounding environment. A number of them have simply just been fenced off. We've built residential areas around some of those. A lot of it comes down to funding. So with some of those sites, people have walked away because at the time there was no regulator, and now who's going to fund the remediation of some of these sites? So yes, I agree. Some of these will never be remediated, but some of the current active sites, these I'm an optimist. So I do think that they will be remediated, because a lot of these companies they need social license to operate as well, and they need to engage with the community. So I think our current active sites, there will be efforts to remediate them.
I think it's a great point, and I know that one of the things that is emerging in sort of the new startup spaces at the moment are companies that are dedicated to things like rehabilitating old mine sites, and particularly being funded through something you were talking about, Andrew, around remining waste and the importance of waste in the whole system here.
Absolutely. A lot of waste rock and mine tailings still have a lot of metal value contained within them, but with the current technology that's being used to process the original ore, it's not economic to try to reprocess the waste. But there are ways, and those are some of the efforts that we're working on now, is to try to actually concentrate some of those critical metals and turn them into a form in which we can recover them from waste.
You also talked about removing CO2 using waste. How much potential is in that?
With our existing technology and at the rate of mining that's currently happening, we could turn the existing waste that has the right minerals in there to remove hundreds of megatons of carbon dioxide. Now, with improvements in technology, if we could expand it to other rock types that are currently being mined, we could get that up to anywhere between 1 and 5 gigatons of carbon dioxide removal. Now, to put that into perspective, each year, at least at the current rate, we emit about 36 gigatons of carbon dioxide annually, and that's still increasing. So it's significant. I mean, it could be 10% removal, but if we decarbonize and remove, because 70% of CO2 emissions come from electricity generation, so if we get that down, we could get a lot closer to net zero. And even if we go net zero, like I said in my talk, we still need to remove residual carbon from the atmosphere as well. So carbon dioxide removal technologies are going to be important even if we don't continue producing CO2.
One of the challenges here too is to try and bring in new ways of mining, so you don't actually even dig it up. So one of our colleagues in our school is Joe Brugger. He's trying to work on biological processing of ores in situ. So the idea is that microbes will break down the minerals into a soluble form that then can be leached out of the rock without even creating mine waste in the first place. So that's one of the challenges to try and figure out how to do as well.
Well, I've been waiting for a bit, and my question's sort of been asked already, because it was around the regeneration aspect. I guess I'm in the same age group as my friend here, and I was teaching a Master of Environmental Science back in the early 1970s, and we were saying the same things. That's 50 years ago. And I guess I'm going to make a question now, which is, what do the students feel? I vacillate between, yes, we're doing some great stuff and things are happening, and absolute frustration and deep concern for my grandchildren. I'll be okay, but they won't. Now, where's the passion in the students? Are they there really feeling that they want to change the world? Do they want to get out and plant stuff to regenerate? Do they want to play with tailings? Do they want to learn the mathematics that they need for the modelling, etc.? I mean, my understanding is that sometimes we've got so many problems with students that they're just lost some of that drive. What's the experience of the panel around that aspect?
So this is probably a good one for several of us to have a go at. I reckon that's a really great question. The students really want to save the world. Actually, they're really worried, and it's actually a source of anxiety for a lot of them that they struggle with. And so for a geologist, that's actually been challenging, because they'll go to the climate school strikes for climate, and they'll be chanting no more mining, not realising the situation we're in. No more mining is great for no more mining coal, but there's a real problem here, as I was saying. So they're really wanting to save the world. So there's plenty of enthusiasm there. We've just got to educate them about how the different ways they can possibly help. And then, so I teach geology. Vanessa teaches climate-related soil science, and Andrew teaches mostly climate-related stuff. Well, environmental chemistry really is the better way to say it, isn't it? Yeah.
Environmental science.
Yeah. So these guys all get quite different students to me. So what do you guys think about that?
There's a new term, a recent term out that's called eco-grief, and we have very engaged students who would like to make the world a better place. So they want to make a difference to the world. But at the same time, I do think we lose students because they're overwhelmed by the enormity of the challenge. And perhaps we've spent too much time telling the doomsday stories without telling the stories about our wins and where the successes lie, because we've been so focused on these big problems. And so perhaps I think one way to address that is to tell the stories, or to present stories of potential solutions, or ways that they can engage to be a part of that solution, so we don't lose a lot of those students who really do want to make a difference. But I know that there are students here tonight, and I'd be interested to also hear from their perspectives too.
I agree with Vanessa. The feedback that I get from a lot of my students is that they want to know more about solutions, and sometimes I think we make a mistake at just always kind of pointing at the problems. It's easy to point out problems, and it's usually a lot more challenging to find solutions to those problems, but the students are really eager to learn about those solutions and how they can contribute to them.
I know you've been waiting a while, please.
Thanks.
Let's hear from you.
I guess I had two questions. The first one's been pretty much answered by Andrew, not Andy, and that was about mine tailings, as far as just thinking from a Victorian perspective, maybe a bit more about pyrite breaking down all the arsenic and mercury and all that sort of stuff, if in the treatment of in the extraction effort of waste stores, if it's possible to actually remove some of the less desirables as well. And the second thing was, I actually caught up with Sandy Cruden yesterday for an hour and a half, and we were just chatting about the teachings of earth science, where you can get an earth science major now where you do not study basically any geology, proper geology. And I was also coming, because I work for a geotechnical engineering company, where the lack of everyone's talking about engineering, but the lack of communication between the engineering and the earth science components at Monash, it's astounding. Where I had a graduate come through the other day and had no idea about soil, anything, like mineralogy, Bowen's reactions theories, anything like that, no idea. So do you think that there needs to be a proper, and this is to the whole panel, that there needs to be more of a proper meshing of the actual teachings with the engineering department properly with regards to soil mechanics and other bits and pieces? And I know we're trying to cram in law and geopolitical stuff and everything as well into that.
So some of the students I teach are science eng students, and some of them are mining engineering students. So they're coming in to learn geology so they can go back and do the mining engineering thing. So they'll learn a little bit of geology when they do that. It's quite hard to cover enough material to really, like if you really want a really good geologist who can work in the minerals industry as an exploration geologist, they would do 8 units at third year to do enough geology. So that's a lot of knowledge, but then you don't learn anything about anything else. So, it's a bit of a tricky balance to strike. What do you guys think?
I think the challenge with engineering is that there's professional accreditation attached to to a lot of their.
With the Washington Accord, and that is currently why I'm looking at doing a master's, and I'm struggling to get a master's where I can use my Bachelor of Science and then be able to get a PE number at the end of it after I've done my master's.
Yeah, so there's limited scope to cram more things into what is now a 3-year degree in science and a 4-year degree in engineering, which requires accreditation for you to practice as an engineer. So I think that's a really big challenge, and it does sort of perhaps come down to postgraduate studies to increase that depth of knowledge.
So we're generally quite happy to teach engineers in our school. It's good for us. We'd like to do more of it.
Well, Sandy said that the engineers have the money, whereas the scientists, especially the physics department, are always poor.
I know there are probably more of you that I can see lots of questions. We have a networking session at the end. I'm running very over time. So what I might do is thank our speakers again for sharing their time, sharing your expertise. I think we've all learnt a lot about how we can and how lots of us do contribute to critical minerals and net zero. There will be a networking session. All of these panellists will be there and are keen to talk to you some more about this. So please take us up on that and stay around with us and join us there. I'm going to bring Udi up just to close out the session for us. Thank you.
No worries. There's been lots and lots of questions, so it's an interesting panel session. So thank you to the moderator and the panellists today, and also to all your questions. Thanks, Janet. And certainly in the networking time, you can certainly ask your questions and fire away. So I would like to give you a gift and say thank you, and then I'll get you to go. Get the panelists to go back and sit down. I've just got a couple of minutes. So put your hands together for our panelists. All right, so before I let all of you go, so I thought I'll take a couple of minutes just to let you know what's coming up next for our alumni. So there's a webinar series that we run. If you haven't tuned in, the next one coming up is on the therapeutic use of viruses to combat the antimicrobial resistant bacterial infections. So on the 2nd of May, 8 to 9, so tune into that. There is a QR code if you would like to register. And if you haven't already joined our Monash Alumni LinkedIn group, there's a chance for you to just join in. It's a great place to stay up to date with the upcoming events, activities, the benefits, and also just meet other alumni, because it's set up as a group. So if you've got any interesting articles in science, please feel free to share. And also, if you're looking for new talent, that's a good place to recruit as well. So that's, I have to say. So thirdly, that's the QR code. Finally, I'd like to ask to give me some feedback after this event, because I'd like to make sure that these events and activities are much more relevant, so it's meaningful for you to come back on campus and also network in the meantime as well with other alumni. So certainly provide me the feedback, and that'll help me sort of, and the teams to work and keep on improving our offerings to you. So that concludes our session for tonight. And I'd like to finally also say thank you to our fantastic panel and also moderator for taking that time. And also to our alumni, guests and students who are here. You guys have been fantastic audience, lots of questions. So I'll ask you to continue your conversations and networking and enjoy some canapes. So thank you. Have a great night.